Okay, so welcome everyone. Thanks for joining us again. So today, for the third occurrence of this seminar in this series, we have Daniel Grumiller from Vienna, and he will tell us about flat space holography and complex SYK.
Okay, yeah, so thanks for having me, and it's a pleasure to be here, even though only virtually. As I said, I've never been to Lyon before, so I hope at some point in the future this is going to be possible again. And today I'm going to report on work done in collaboration with two former postdocs at TU Wien, with Hamid Afshar and Hernan Gonzalez, and also with a longtime collaborator in Brazil, Dima Vasiljevic. And yeah, I'll tell you about flat space holography and the complex Sajdiv-Yeki-Taif model. And the beginning of my talk will be mostly motivational and introductory. So I'll start with a motivation, why we're interested in studying BMS2 in the first place. Then I focus on kinematical aspects and BMS2. And then in the main part, I show you dynamics yielding a BMS2. So I show you a concrete gravity model whose asymptotic symmetries are going to be BMS2. And in the last part, I'm going to use this information to relate this model to a specific condensed matter model, and that's in turn related to the SYK model. And the SYK-JT correspondence has led to lots of excitement and developments in the past 5 years. And in some sense, the aim of our paper is to provide the flat space counterpart of such a correspondence. Okay, so let's start with motivation, and I'll start with asymptotic symmetries. So this is the introductory part, and if you have heard my talk in Brussels, then, well, you know everything that is going to be presented on this and the next couple of slides. But I'll be shorter in my review part than in my Brussels talk in last fall. So if you hear these things for the first time, then, well, you should probably consult some literature. Anyway, let me start. So if you learn the first time about quantum field theory, then usually you impose implicitly or explicitly natural boundary conditions, meaning that all your fields either have compact support or vanish sufficiently fast as you approach the asymptotic boundary. And this is, of course, not applicable in gravity because the metric must not vanish asymptotically. So when we have gravity or also gauge theories in presence of actual or asymptotic boundaries, we encounter asymptotic symmetries, and they're defined to consist of all boundary condition preserving transformations modulo proper gauge transformations. So a simple way to implement this in the context of gravity is by explicitly choosing some boundary conditions on the metric. It's not necessary, but often very convenient to introduce some adapted set of coordinates. So here I'm not specifying very much. I'm just assuming that there is a radial coordinate that is convenient. I call it R. And it's defined in such a way that the boundary is an isosurface of this radial coordinate. And the radial coordinate R takes the value RB at the boundary. So that value could be infinite in some examples. And the remaining coordinates I just call boundary coordinates. And the left-hand side of this equality consists then of all metric that are compatible with the boundary conditions. And on the right-hand side, you have a split into an asymptotic background metric, G bar, which is not allowed to change. And then there are fluctuations that are permitted by the boundary conditions in delta G mu. And I color code this in this way. So blue is any metric that is compatible with the boundary conditions, and green is any fluctuation that is permitted by the boundary conditions. And the boundary condition preserving transformations are then generated by so-called asymptotic killing vectors xi, which are defined by the following equation. So if you act along this vector field xi with the lead derivative on any metric that is compatible with the boundary conditions, then the result must either be 0, or if it's not 0, it must be of the order of the Laut fluctuations. So as opposed to ordinary killing vectors, you can have infinitely many killing vectors, even in low dimensions. And typically, these asymptotic killing vectors can be expanded radially. So you can expand these asymptotic killing vectors xi into a leading order part, which again typically generates the asymptotic symmetries. So those diffeomorphisms that are not proper diffeos but improper diffeos, they can change the physical state. And there are some non-trivial and non-vanishing boundary charges associated with this. And then there are subleading terms which generate proper diffeos, and they are modded out in the asymptotic symmetries. And relatedly, the definition of the asymptotic symmetry algebra is the Lie bracket quotient algebra of the asymptotic killing vectors modulo the proper diffeomorphisms. And yeah, in case you hear this for the first time, here's some references. So there are different formulations you can use to describe this. There's the covariant phase space method. For reviews, you can look at these papers here. For instance, the lecture notes by Geoffrey Compere and Adriano Fiorucci. And there's also the canonical analysis that leads to the same conclusions. And a related issue to asymptotic symmetries are the existence of boundary excitations or edge modes. In the context of gravity, they're also often called boundary gravitons. And these edge modes are a feature of gravity or gauge theories, particularly topological gauge or gravity theories, in the presence of non-trivial boundaries, for instance, in quantum Hall systems. And the physical explanation of these modes is that even though there are no local excitations in the bulk, the boundary conditions are so non-trivial that there can be physical degrees of freedom that you can visualize to be localized at the boundary. And in the gravity context, there's recent work by the Lyon group in collaboration with Perimeter Institute. So in my talk, I'm interested in a very specific aspect of asymptotic symmetries, namely in the context of holography. So the best known example of implementing holography is the anti-de Sitter conformal field theory correspondence. And the asymptotic symmetries are a basic ingredient in ADS-CFT for any test of holography that is based entirely on symmetries. So for instance, the calculation of 2-point and 3-point correlation functions, or the calculation of thermal entropy in ADS3-CFT2 context, or also the calculation of holographic entanglement entropy. This is entirely determined by the asymptotic symmetries, plus the value of the central charges, if there are any. And therefore, knowing the asymptotic symmetries is quite important for these tests. Moreover, the asymptotic symmetries captures universal UV features of the dual quantum field theory. So in the ADS-CFT context, these are conformal symmetries of the UV conformal fixed point CFT. And in the lower dimensional context, so in ADS3-CFT2, there was an important precursor of this correspondence in the seminal work of Brown and Deneau. So in some sense, Brown and Deneau showed already that Einstein gravity in 3 dimensions with negative cosmology constant and their boundary conditions, if it exists as a quantum theory, it must be dual to a conformal field theory in 2 dimensions, in the sense that the physical Hilbert space falls into representations of 2 copies of the Virasoro algebra. So in my talk, we want to go one step beyond the canonical ADS-CFT correspondence. We're interested in flat space holography. And there were a lot of developments actually in the past decade on flat space holography in 3 dimensions, so in 3 bulk dimensions. And also there it turned out that asymptotic symmetries, not surprisingly, are a basic ingredient of flat space holography and of any tests based on symmetries. So again, correlation functions, thermal entropy and entanglement entropy are largely constrained or essentially uniquely determined by these symmetries, again, up to the values of the central charges. Now, in higher dimensions, the flat space symmetries, the so-called BMS symmetries, capture universal infrared features of quantum field theories in flat space. So this is due to work by Andy Strominger and collaborators that relates the word identities associated with BMS symmetries to sort of theorems. And 20 years after the Brown and Deneau work, there was a corresponding work in 3 dimensions. So the Barnich-Compare analysis was an important precursor for the correspondence between flat space Einstein gravity and Carolian conformal field theories in 2 dimensions. Now in my talk, I'm going to focus on flat space holography, but let me nevertheless briefly say a few words beyond this. So a long-term research goal is to understand how general is holography and does it work beyond ADS-CFT. So in that context, it's again important to know what are the asymptotic symmetries on the gravity side. Can we do asymptotic holography beyond ADS-CFT? That's one, I think, interesting question. If it's always possible, how does it work precisely? If it's not always possible, what are the criteria that make it possible? And inspired by this proposal by Hawking, Perrin, Strominger on software, one can also ponder about near horizon holography. I will not talk about this in my current talk, but that's again an interesting step beyond the canonical setup. So in all these cases, it turns out that asymptotic symmetries are important input for the structure of the dual quantum field theory, assuming there is one. So that's why we're interested in studying the symmetries from a holographic perspective. So now let me come to particularly flat space, so Bms4 as a first example. This was also historically the first known example of non-trivial asymptotic symmetries. And here I give a brief history. So I'm not a science historian, so I'm not trying to reflect the actual history very precisely, but I think it's a correct statement that until the 60s, the general sentiment was that general relativity in the limit of low curvature must be identical to special relativity. And the reason why most people believe this is because it's very plausible. If you set the, all your curvature invariants to 0, and you end up essentially with the Minkowski metric, then you would expect to reobtain the symmetries associated with the Minkowski metric, so just the Poincare symmetries. However, this is not what happened. So famously, Bondi, van der Burg, Metzen, and Sachs showed in '62 that this is not the case. You get an infinite extension of the Poincare symmetries by super translations. So you get much more than Poincare symmetries. You get an infinite tower of translation operators or generators that commute mutually with each other. So P is how I denote the super translations. X are angular coordinates of the celestial two-sphere. And super has nothing to do with supersymmetry. It's just, I guess, the spirit of the sixes to call things super. So it just refers to the fact that you have infinitely many of them. And in my talk, I know that some people have a more geometric approach to everything in life. My approach is a bit more algebraic, so you will see few diagrams and more algebras. So I apologize to those people whose brain is more geometrically wired, but yeah, it's a very concise way of conveying information. So here's the Bms4 algebra. JA generates diff S2 or some restriction thereof. Sometimes they're also called super rotations. And the P's are the super translations, and as you can see, they mutually commute with each other. J with P does not commute. It commutes into something proportional to P with some structure constants that depend on the spin of the super translation. And J with J forms a subalgebra that generates diff S2. And in the original Bms4 work, the spin was 1, but there are generalizations to other spins. For instance, in the context of near horizon symmetries, you find the same type of algebra. And in this very nice work by Laura and collaborators, they found a version of this algebra where you have scalar super translations, where the spin is 0. And in the work with Celine Zwickel and collaborators, we generalized this to arbitrary spin S. But again, I'm not going to talk about near horizon symmetries in the rest of my talk. This was just a side note. So this is my summary of Bms4. Let's now slowly descend in dimensions. So let's go to 3 dimensions. So in 3 dimensions, there is actually a very efficient way of obtaining the flat space symmetries from the anti-de-Sitter symmetries. And since I'm going to use a similar technique later, let me get into some detail. So this is, for instance, done in work by Barnich, Komarov, and Gonzalez in 2012. So you start with the symmetries of ADS3, which are 2 Virasoro algebras, which are denoted by this calligraphic L and L bar. And then you make a change of basis. So you define new generators Ln and Mn, which are just linear combinations of the L and L bars. And in Mn, I introduce some parameter 1 over L. And as long as this is finite, it's just an ordinary change of basis, slightly weird change of basis perhaps. And in this new basis, the Virasoro algebra takes this form here. So L with L forms again a Virasoro algebra with a central charge that is the difference of the original ones. L with M forms, well, is a commutator that on the right-hand side looks like it was a Virasoro algebra for the M's with the central term that is the sum of the original central terms rescaled by 1 over L. And M with M gives something that is non-zero as long as L is finite. And now comes the non-trivial step. So now we're interested in the flat space limit. The quantity L you can think of as the ADS radius. So cosmology constant to 0 corresponds to ADS radius going to infinity. And in the limit where the ADS radius goes to infinity, this last commutator here vanishes. So that means we get an inner-Wigner contraction, we get a different algebra, but it emerges from the original algebra in this simple way. And this is indeed the Bms4 algebra, where the MNs now play the role of super translations and the Ls generate super rotations or diffs1. Now, a concrete example is Einstein Gravity. In Einstein Gravity, in anti-de Sitter space, you find the Brown and no central charges. C is equal to C bar is 3L over 2G, where G is Newton's constant. And when you insert this into these results of the contracted central charges, you find that after the Wigner contraction, there's no Virasoro central charge, but there is a mixed central term in this BMS algebra. So on the next slide, which I'm not going to discuss in detail, I just mention some historically important papers, like this first one by Ashtek and collaborators, and the second one by Glenn and Geoffrey, and also some examples of developments and checks of holography that were achieved in the last decade. So this is just to show you that there was a lot of development of flat space holography in 3 dimensions in the past decade, and this is still an ongoing research subject. But one thing this is missing, so with one exception, with the exception of this proposal of flat space chiral gravity, we don't have a very precise understanding of what is the dual field theory, apart from it being a Carolian CFT2, but not which Carolian CFT2 precisely. So it would be nice to advance the subject of flat space holography to have a very precise and concrete correspondence available. And this is one of the motivations to go down in dimension even further, to go down to 2 dimensions. So here are my motivations for BMS2. The first one is just, you know, the eternal motivation of curiosity. Maybe there's something like BMS2, and if so, it would be interesting to study it and see what it's good for. What it might be good for is for toy models of flat space holography. So if there is something like BMS2, it should feature prominently in these lower dimensional models of flat space holography. And perhaps it's also useful for near horizon holography, just on the grounds that for many applications, essentially only a 2-dimensional slice of space-time matters, and the transversal directions on the horizon may not be so relevant for the kind of questions that you're asking. And finally, a very concrete motivation is the aim to construct SYK-like models, but with an asymptotically flat gravity side. So here I have stolen one slide from Douglas Stanford's talks at Strings 2017 in Israel, which defines the SYK model as a strongly acting quantum system that is solvable at large n. N is the number of fermions. And this has applications to black holes, to chaos, to ADS2, and strange metals, among other things. So one motivation is to try to find a flat space version of these SYK models. Okay, so before doing this, before starting, let me also point out some potential difficulties. A general point in 2 dimension is that codimension 2, which is the dimension of relevance for your boundary charges, they're always codimension 2 charges. So codimension 2 is structureless in 2 dimensions, and well, you might be worried about this, but it's sort of okay in the ADS2 context, so maybe it's also sort of okay for BMS2 as well. Another issue is that it's very easy to get the ADS2 algebra from the ADS3 algebra. You just take 1 chiral half and then you're done. But the same cannot be true for the relation between BMS2 and BMS3, because there's no natural way to split the BMS3 algebra into 2 chiral halves. So, you know, that just means we have no quick way of cheating towards BMS2. We have to do a proper analysis in 2 dimensions. Another issue is that if you care about super rotations, then they can only be in time direction because, well, basically because of the first point, the boundary doesn't have enough structure. There's just a time direction. There are no additional angular direction into which you can rotate. And that is okay. So either you don't care about super rotations at all, and if you care about them, you can still have them at least in the Euclidean theory or something analog to them. And finally, perhaps the most severe potential difficulty is that, again, there's not enough room for super translations in the proper sense, because you cannot have angle-dependent translations if there are no angles, which is the case in 2 dimensions. So therefore, if you have something like super translations, they can only be radial super translations, and it's not obviously from the beginning whether this makes sense, whether the associated canonical charges will be non-trivial, etc. So these are potential difficulties, but you know, perhaps they can be overcome. So I'll take a very pragmatic attitude, quoting Peter van Nieuwenhuizen, that the task of theoretical physicists is to break noble theorems. So let me just, you know, ignore all these potential difficulties and proceed and be optimistic and hope that it works. Okay, and in fact, it is going to work. Let me start now with the kinematics. So by kinematics, I mean, I just look at metrics and their fall-off behavior and determine the asymptotic killing vectors, but I don't care at the moment whether these metrics appear in any meaningful gravity theory. So we're interested in 2 dimensions, which is very simple. There's only one scalar invariant that you can construct out of the Riemann tensor, namely the Ricci scalar. So we're interested in asymptotically Ricci flat metrics. One potential way to define asymptotic flatness locally is to demand that the Ricci scalar tends to 0 sufficiently fast in 2 dimensions. And I'm going to use a gauge fixing to Eddington-Finkelstein coordinates. It's not obvious that this is possible with proper gauge transformations. And in fact, we know that it need not be possible. So we are losing some potential information, some edge states or symmetries that we could have had. But as long as what remains is still interesting enough, this is okay. And I should say that the same remark applies actually to any gauge fixing that you do a priori, also in ADS3. So if you want the most general set of boundary conditions, the best attitude is not to gauge fix at all and try to come up with the most general analysis. But here we are fine if there is something interesting going on already in this restrictive setup. So demanding Ricci flatness means that this function k of u and r in the UU component of the metric can be at most linear in the curvature. So that means k of u and r is some function that is, for convenience, 2 times p of u times r plus 2 times t of u. And p and t are arbitrary, in principle, state-dependent functions. If they're constant, then you can easily spot that there's a killing horizon, RH at minus t over p. And for simplicity, most of my talk, you can assume that p and t are constant, even though everything that I say, or most of what I say, generalizes to the case when they're functions of u. So that means the boundary conditions that we want to impose are to restrict to metrics of this type with functions k that are linear in R and functions p and t that are allowed to fluctuate arbitrarily. So whatever the gravity theory is going to be, we require the following boundary conditions for the metric. So we have a linear term in R, a order 1 term, and in principle also subleading terms that vanish as R goes to infinity. So this is our operational definition of asymptotically flat, locally asymptotically flat metrics in 2 dimensions. Okay, so let's proceed with this. Let's assume this makes sense. Our next task is to determine the asymptotic killing vectors. Well, this is straightforward. So this class of metrics is preserved by asymptotic killing vectors of this form. So it's a good sign that we have infinitely many of them. They're labeled by 2 arbitrary functions, epsilon of u and eta of u. And epsilon of u generates the 2D analog of superrotations. So if u would be compact, so say we are on the disk, then this generates diff S1, otherwise just diffeomorphisms of the real line. And eta of u generates super translations, or an analog of super translations. You are justified to call these translations because all these generators commute with each other. And I call them radial super translations because, well, the translation is in the direction of the radial coordinate. And instead of angle dependence, we have this u dependence of the function appearing as a prefactor. Now, interestingly, these metric functions P and T transform non-trivially under these super rotations and super translations. And if you're a bit familiar with structures of 2-dimensional conformal field theories, then you may recognize this transformation behavior, or at least you probably have seen similar transformation behavior, perhaps with slightly different anomalous terms. So this looks rather promising because P transforms like a U1 current. So the first two terms show it's a weight 1 conformal quasi-primary. And the appearance of the last term shows it's not a primary, but a quasi-primary, because there's this anomalous term proportional to epsilon double prime. I'll come to this in a bit more detail later. And T transforms like a spin 2 current or like a Virasoro generator, but again, there's a difference to standard Virasoro generators. So there's no epsilon triple prime term, so there's no standard Virasoro central charge appearing. But nevertheless, there is an anomalous term, and again, I'm going to address this a bit later. At the level of the Lie bracket algebra of asymptotic killing vectors, of course, there's no central extension. So this is the Lie bracket between two asymptotic killing vectors, and of course, it closes into another asymptotic killing vector of that form. And it's, again, a bit easier to recognize what this algebra does if you go to some modes. If you are on the disk, you can go to Fourier modes. Here, that means that introduce Laurent modes. So Ln is the nth or n plus first Laurent mode of epsilon, and m is the n minus first Laurent mode of eta. And the corresponding algebra of these modes is displayed here. So the L's form a subalgebra, namely a width subalgebra. The M's commute among themselves. So this shows consistently that indeed they are super translations. And the middle commutator shows that, or Lie bracket shows that these are like spin 0 super translations. So if you interpret this again as a quantity with a certain spin, then you deduce that the spin is 0 of these generators. So this algebra is what I call Bms2. And let me just point out that algebraically, you can find, in principle, non-trivial cocycles of that algebra. So this algebra is allowed to have non-trivial central extension, and we will later see in a concrete model that there is going to be a non-trivial central extension. Before discussing the dynamical aspects and presenting a concrete model that realizes these symmetries as asymptotic symmetries, let me address a global aspect that is of some relevance, and you will see what it means physically a bit later. So let me, just for fun, redefine the function that generates super translations in this way. So instead of eta, I use now sigma, but the relation is by taking a derivative. So eta is sigma prime, or sigma would be the integral of eta. So this is not just a change of basis. It's a bit like a change of basis, but something non-trivial happens to the 0 modes, as we shall see in a second. And now I can also do the same, or implement the same redefinition at the level of the mode. So I introduce Laurent modes Jn with respect to modes of this function sigma. And in terms of Jn, I find that the J's are again super translations. And of course, nothing changed in terms of L's. But L with J now has a different spin. So we have a spin 1 super translation set of generators. So this algebra is, again, well known in CFT literature. It's sometimes called warped width algebra. And the relation to the old super translations is as follows. So Mn are the old super translations, the spin 0 current, and the Jn are just n times Mn, as long as n is not equal to 0. So this is almost a basis change. You can map all the Jn's to Mn's and vice versa, as long as n is not 0. But you cannot map the 0 modes because J0 is mapped to 0 by this map, and nothing maps to M0. And that's, again, a consequence of the fact that you have this differentiation appearing here. And later we'll see that M0 is interpretable as a winding mode of a Maxwell field. So for most of my talk, I'm going to dismiss this winding mode and focus instead of the warped width algebra. So up to this issue of 0 modes, we can use interchangeably the Bms2 algebra or this warped width algebra. And in my talk, I'm going to focus mostly on this warped width algebra.
Daniel?
Okay, so this is now the first part of my talk, so the kinematics. And now let's focus on the dynamics. So now our task is to find a specific gravity model whose asymptotic symmetries are equivalent to the Bms2 symmetries. and perhaps with some central extension when we canonically realize the asymptotic symmetries. The model space that we are considering is dilaton gravity in 2 dimensions. So a candidate theory of gravity that realizes our boundary conditions is Einstein dilaton Maxwell gravity in 2 dimensions. I'm referring to this paper with Jakob because there we discuss also the boundary contributions to the action in the second order formulation. So the class of actions that we're interested in is given here. So we have the following second order action. We have, well, 2-dimensional Newton's constant as a coupling constant. Then we have a scalar field that I denote by x, and this dilaton, as it is called, is defined by its coupling to curvature. So I define in such a way that the coupling is always x times r. Then there's a kinetic term that contains a coupling function u of x, and there's a self-interaction potential v of x that leads to non-trivial geometries when it's non-zero. And in a holographic context, it's often important to also take into account the boundary contributions. For instance, if you want to evaluate the on-shell action to derive thermodynamical quantities like free energy. Okay, I'm sorry, there's some construction going on in the room next to mine. Okay, let's stop. Okay, so yeah, these boundary terms can be important if you want to evaluate free energy, for instance, from the on-shell action. And the first term is well known. That's the analog of the Gibbons-Hogg-York boundary term in the presence of a dilaton field. So this guarantees that you have a well-defined Dirichlet boundary value problem. And the second term is a holographic counter term. This is a bit less obvious. So in the case of dilaton gravity, it turns out that this is essentially given by the superpotential, so a somewhat bizarre looking combination of the potentials u and v. And the presence of this term guarantees a well-defined variational principle. So the first variation of the action vanishes for all variations that preserve certain classes of boundary conditions. There's a lot of fine print, but I don't want to get into this. I just want to point out that it's important to add these boundary terms if you want to derive the free energy from the on-shell action. And in our case, we also want to couple dilaton gravity to matter, which is in general an interesting option. And we are very specific, so we couple 2-dimensional dilaton gravity to an abelian Maxwell field, so to a Maxwell field. So we have f mu, where f mu is the abelian field strength, and we allow in principle also for a coupling function f of x to be general. Okay, so we have an infinite set of models available, labeled by these functions u, v, and f. Clearly that's too much, so let's just have a brief look at a selected list of models. I'm not going through the whole list. I just want to point out that some of the models lead to black hole solutions in anti-de Sitter space or de Sitter space, like the famous Chakif-Teitelbaum model, which is one of the simplest models of 2-dimensional dilaton gravity. There's no kinetic term, and the potential term is just linear in the dilaton. But there are also models that lead to asymptotically flat, or even some arbitrary asymptotically behaved spacetimes. And we're interested in asymptotically flat spacetimes. So for us, the models in green are the important ones. And the simplest ones of those is the CGHS model, which again has vanishing kinetic term and a very simple, namely constant potential V. So for simplicity, we're just going to focus on this fourth line here on the so-called CGHS model. Now, from now on, I'm going to present a bit more technical details because I know at least some people in the audience might be interested in them. So in order to proceed, I'll switch now from the metric formulation to the gauge theoretic formulation as a Poisson sigma model. So in Lyon, you have one of the founding fathers of this formulation, namely Thomas Strobel. And well, in some sense, Poisson sigma models are the 2-dimensional analog of John Simon's formulation of 3D gravity. The main difference is that these gauge theories are in general nonlinear. So that's, of course, a generalization of standard Yang-Mills type of gauge theories. However, it turns out that for applications to Chakif-Teitelbaum gravity and also to the CGHS model, you can get away with the simpler case of linear but non-abelian gauge theories. So then, actually, instead of having to use a Poisson sigma model, I can use an even simpler class of models, namely non-abelian BF theory. So the bulk action is given here. The BF action depends functionally on some coadjoint scalars B and on some connection one form calligraphic A, and it has a coupling constant kappa that is essentially 1 over Newton's constant in a gravity context. The brackets here denote the invariant bilinear form, and F is the non-abelian field strength associated with this non-abelian connection A. BF theory in general has nothing to do with gravity, but if you want to have a gravity interpretation, then you have to choose the connection form, one form essentially as follows. So the connection one form consists of a spin connection part. That's a special feature of 2 dimensions, that you can dualize any metric compatible spin connection with the epsilon symbol to a quantity that has no indices except for the form indices, which I suppress. And the spin connection comes together with the generator of Lorentz boosts. Then the translation generators come together with the Zweibein, and the Maxwell connection has an extra abelian generator set. And we similarly decompose the scalar field. The dilaton appears in the Z component, and then there are 2 or 3 rather auxiliary fields, XA and Y. So this is just a general structure of a BF theory that may have a gravity interpretation. We need to encode somewhere the spin connection and the Zweibein, and if we have a Maxwell field, also the Maxwell field. But we still need to be more specific and choose the gauge algebra and the bilinear form. So it turns out to obtain flat space gravity models that have a BF formulation, we need to choose the Maxwell algebra. So this appeared first in the Kangemi-Chakif version of the Kalan-Giddings-Harvey-Strominger model. The Maxwell algebra is essentially a Poincare algebra, but with a central extension between the translation generators, and the bilinear form compatible with the Jacobi identities is given here. So it's non-degenerate and symmetric. Now, if you integrate out the auxiliary fields XA, which you can think of as Lagrange multipliers for the torsion constraint, and you integrate also out the spin connection, then you end up with this mixed second first order action where we have the metric and the dilaton, but also this auxiliary field Y and the Maxwell connection. And this is the action, the bulk action that we're going to focus on. So this is the Kangemi-Chakif version of the CGHS model. The equations of motion are very simple. If you vary with respect to x, you get r is equal to 0. So you immediately see that we're not only locally asymptotically flat, we are actually locally flat everywhere. So this is very reminiscent of how pure Einstein gravity works in 3 dimensions. If you have a negative cosmology constant, for instance, then any metric that solves your classical field equations is not just locally asymptotically ADS, it's also locally ADS. Okay, but we have more field equations. So if we vary with respect to y, we get an equation that essentially tells us that the electric field associated with the Maxwell field is constant and fixed. And then when we vary with respect to the metric, we get a dilaton equation of motion, and varying with respect to the Maxwell one form establishes that y has to be conserved and constant on shell. So it's some constant lambda. Okay, now in order to proceed further, we need to translate our boundary conditions into this BF formulation. So I presented to you boundary conditions on the metric, but I have to translate this to you into this BF language. Yeah, again, I'm sorry for the noise, but it stopped again. So there's some construction going on apparently. Okay, anyway, so the ansatz that worked already nicely for the Chakif-Teitelbaum model, and that is very much inspired by how you can impose boundary conditions in the Chern-Simons formulation in 3 dimensions, is given here. So we split the full connection, calligraphic A, into a group element B that captures the radial dependence of our connection, and that is state independent. So B is just exponential of minus R times one of the generators. And then we have a boundary connection, small a, that has only legs in the boundary directions. So in our case, there's only one direction, namely u. And also the functions appearing here depend only on the boundary coordinate, which in this case is u. And it turns out in order to get our boundary conditions on the metric, you have to pick the boundary connection A in the following way, where T and P are the 2 state-dependent functions that appeared earlier in our discussion of asymptotically flat metrics. Okay, and you do a similar thing for the scalar field. So also this scalar field B is decomposed into a boundary scalar field X and this same group element B. And our boundary conditions allow for arbitrary variations of T and P. Now, it's a simple exercise to check that with these boundary conditions, the metric is precisely of the form as I've shown before. The dilaton is an arbitrary linear function of the radial coordinate. So that explains why often in a string theory context, these solutions are known as linear dilaton vacuum. And the Maxwell field is just the Coulomb field in two dimensions. So in two dimensions, the Coulomb field is confining. So it's just a linearly rising potential. A is R du. And it turns out that indeed we obtain the Bms2 asymptotic symmetries that I showed to you earlier. Now, this is not completely evident because we have now not only the metric to consider. For the metric, this is definitely true. We know already what are the asymptotic killing vectors. But we have to check that the same asymptotic killing vectors preserve also the boundary conditions on the scalar field and on the Maxwell field. For the scalar field, this is a triviality because we have arbitrary functions of u here, so there's no further constraints. But for the Maxwell field, this is not so obvious because, well, we have to recover and maintain this Coulomb form of the potential. And actually, there are two conflicting expectations that you may have at this point. You could either argue that perhaps the asymptotic symmetries are larger than Bms2 because you have additional U1 gauge transformations available. So perhaps these additional U1 gauge transformation enhance the Bms2 symmetries. At the same time, you can argue that, well, because you have to maintain this form of the gauge connection, perhaps you get a sub-algebra of the Bms2 algebra because maybe not all the Bms2 symmetries preserve this form. And it turns out that both expectations sort of cancel each other. So what you end up with is precisely the Bms2 symmetries. And what happens is that the Maxwell field is preserved by a combination of diffeomorphisms and gauge transformations. So you act simultaneously with a diffeo and the gauge transformation. And you have to fix the gauge transformation entirely in terms of the data contained in the diffeomorphism. So to be more concrete, you have to choose the sigma in such a way that eta is equal to sigma prime. So it means that the U1 gauge transformation is not independent from these super translations. And now we come back to the issue I mentioned a bit earlier. So we have indeed now a relation sigma is eta is sigma prime. So that either means that eta has no zero mode, if we want sigma to be regular and single valued, or sigma is not single valued. So if we allow eta to have a zero mode, that means that sigma prime must have a zero mode, but that means that sigma cannot be single valued. So in that case, we do get winding modes. So the interpretation of introducing the sigma instead of the eta is that we introduce winding modes for the Maxwell field. But in my discussion today, we're going to focus on the case when there are no such winding modes. So again, instead of Bms2 symmetries, we get the warped width algebra. Okay, so we see now that we do get the Bms2 symmetries or the warped width symmetries. What can we do with them? Well, our next step was to discuss the boundary action, which we call twisted warp boundary action, and which I explain what it is on this slide and why it is of interest. So when you vary the BF action, for now, or from now on, I'm using Euclidean signature, so T is I times U. You find that the variation of the action doesn't vanish on shell, you get a boundary term. So in order to repair this, so that you have a well-defined variation principle, you have to add a boundary term. And that boundary term is precisely the boundary action we are after. So this is this twisted warp action. And the physical interpretation of that action is that on the gravity side, it describes essentially the dynamics of the edge modes. So it's a bit like the Liouville action in the context of ADS-free gravity, or the Schwarzian action in the context of the Chakif-Teitelbaum SYK correspondence. And on the field theory side, which I address at the very end of my talk, this twisted warped action describes the dynamics of the collective low temperature modes in the large limit. But we're not there yet, so for now, let's not bother with holography. Let's just focus on the gravity side. So we follow at the technical level, very much the Chakif-Teitelbaum story in the BF formulation, which you can find in this paper with Ernan and Jakob. The derivation of this boundary action was obtained earlier than this, of course, but in that work we did it in the BF formulation, which is very useful because it allows you to generalize more uniformly to other theories in the BF formulation, in particular to the current model, to the CGGS model in the Kangemi-Chakif formulation. Well, and the end of that calculation is this action. I'm not presenting you details of that calculation. I'm just showing you the final results. You get a boundary action. It's a one-dimensional action that depends functionally on two fields, H and G. H you can interpret as a time regularization field, and G is a phase field. And we're integrating over one cycle. So we're assuming here now that we're on the disk. So we have periodicity beta, where beta you can interpret as the inverse temperature. Prime here means derivatives with respect to tau. Kappa is again the same coupling constant as before. T and P are these state-dependent functions. And you can see that you have not just first derivative terms, but also second derivative terms appearing. So this is a bit reminiscent of the Schwarz in action. If you have seen the Schwarz in action already, then you recognize that this is somewhat similar, but it differs in some details. In particular, in the Schwarz in action, you have up to third derivatives appearing, and here we only have up to second derivatives. So what's the interpretation of this action in algebraic terms? Well, this twisted warp action is the flat space analog of the Schwarzian action. So if you have a good understanding of what the Schwarzian action is, you can immediately apply this understanding to this twisted warp action and just replace ADS2 by flat space in 2 dimensions. So in case you're unfamiliar with what the Schwarzian action is about in these algebraic terms, the Schwarzian action is the group action for Virasoro coadjoint orbits. So if you've never heard about this, I recommend you read this very nice paper by Alexeyev and Chatashvili from the 80s, or more recent work on SYK JT correspondence, where these Virasoro coadjoint orbits are reviewed. And our action is the flat space analog, so it's the group action for twisted warped coadjoint orbits. Now, the algebra associated with this Virasoro coadjoint orbits is the Virasoro algebra. The algebra associated with this twisted warped coadjoint orbits is this algebra. So it's the same algebra that we've seen before, the asymptotic symmetry algebra generated by the asymptotic killing vectors, except there's now a central extension, and it's a slightly unusual central extension. So if you've seen this type of algebras, you may have been familiar, you may be familiar with the central extension that you can have here, the Virasoro cocycle, or the central charge that you can have here, the U1 level. But in our case, we have neither of those. Instead, we have these twist terms, where the term in the mixed commutator that is a non-trivial cocycle, and it's proportional to the same coupling constant kappa that appears in front of the action and then also in front of the bulk action. And if you act with asymptotic symmetries on this twisted warped boundary action, you find that H and G transform like boundary scalars under diffeomorphisms, and additionally, G transforms like a phase under U1 transformation. So they have well-defined transformation behavior under your asymptotic symmetries. And as I'm going to show in a bit more detail, this twisted warp action resembles the effective action for complex SYK. So this will be the remaining goal of my talk, to show you in which sense this is true and what is the precise relation to the complex SYK model. Okay, so I have about 10 minutes, so that should be sufficient. So let me start with presenting the Hamiltonian formulation. Since we have up to second derivatives, it's convenient to introduce auxiliary fields so that you have a standard first order action of Hamiltonian form. And when you do this, you find this is the twisted warped action in the Hamiltonian form. So there are a couple of auxiliary fields. And if you are familiar with the Schwarzian action, again, you will recognize the similarities. So here's the Hamiltonian version of the Schwarzian action, again, with some auxiliary fields. And you see the only difference between the two is that the kinetic term here is given by P1 squared, whereas here it's a bilinear P1, P2. That's the only difference, but it's a crucial difference. And well, you can treat this as a simple mechanics problem. You can find the Hamiltonian equations of motion, you can solve them, you find 5 integration constants, and 2 of them appear in this quantity P, and the remaining 3 in this quantity T. So in particular, P is independent of all the quantities that are denoted by G. This will be important on the next slide. Okay, and when we now evaluate the on-shell action, so we take the twisted warp action, we evaluate it on-shell, then we find that this is just given in terms of one of these constants, namely the constant G1. So that's the constant that appears in this non-periodic term. Okay, why is the value of the on-shell action of relevance? Well, it's of importance for a very interesting thermodynamical observable, namely entropy. So if we assume that the constant G1 is independent from temperature, we immediately get the entropy is just given by minus the on-shell action. So it's 2 pi kappa times G1. Can this make sense? Well, if you use the result for the dilaton using the equations of motion, you find that G1 is the dilaton evaluated at the horizon, so that this formula here essentially reads that the entropy is given by the dilaton evaluated at the horizon. And this is indeed a well-known standard result in generic two-dimensional dilaton gravity. You can easily obtain this by applying, for instance, Wald's neutral charge technique to deduce the entropy for two-dimensional dilaton gravity. And then you find it's the dilaton at the horizon. So this makes sense. And in fact, you can derive this assumption here, so you don't have to use it as an assumption, from regularity conditions. So like in ADS-free gravity, where you assume absence of conical defects in the Euclidean formulation of the theory. And in this case, this leads to the condition that P, the state-dependent function, on shell must be given by 2 pi times the temperature, but this calligraphic T is arbitrary. So since P is independent from G1, that means that G1 is indeed independent from temperature. And this is what we assumed here, and here we show that this assumption is correct. So the physical interpretation is that P is the U1 charge while T is the mass. And I'm mentioning all this because there is a peculiarity of this model. It's again a well-known property of the CHS model, but if you're not familiar with this model, you may not know this. So the inverse specific heat vanishes for the CHS model. So indeed, if you evaluate the inverse of specific heat, so C2 minus 1, dt by ds, well, since this doesn't depend on S when we keep fixed P, the result is 0. So that means that we have actually a useful thermodynamical property that we can try to exploit for obtaining our model as a scaling limit from complex SYK. We need to make sure that the specific heat tends to infinity. Okay, so let's do this. So here's finally the low energy effective action of complex SYK. So if you're unfamiliar with SYK, again, I recommend you watch Douglas Stanford's talks that I referred to earlier. And the complex SYK is very nicely reviewed and discussed in this paper by Gu, Kitaev, Sachdev, and Tarnopolsky not too long ago. And they showed that the effective action that governs the collective low temperature modes is given by this action here. So let me unpack this. The braces denote the usual Schwarzian derivative. So this last part is the famous Schwarzian action. N denotes the number of complex fermions. So you have a system of randomly interacting complex fermions. And in order to be able to apply holography, to have a good gravity interpretation, you need to take the large N limit. So you assume there is a large number of these fermions. Now, when you do a thermodynamical analysis of this model, you find that the parameter determining specific heat at fixed charge is N times gamma, so it's this prefactor in front of the action. And the other quantities also have some meaning. K is called the zero temperature compressibility. This calligraphic E is the spectral symmetry parameter, and the functions H and G, on which this action depends functionally, are again a time recompensation field and a phase field. So they have the same interpretation as in our flat space model, which is encouraging. And they also have the same periodicity properties. So H is quasi-periodic and G is periodic in the absence of winding. So if we want to have a chance to obtain our twisted warp action from this action, we need to make sure to get the right thermodynamics. So we need to send the specific heat to infinity. So we need to send N times gamma to infinity. And in order to do this consistently, it turns out that additionally you need to take the limit k to 0 in such a way that the geometric mean essentially stays constant. So I'm not showing you the details of taking this limit. It's a bit subtle, but you can find the details in the paper. But when you take this limit, you find that the complex SYK boundary action indeed turns into our twisted warped action, where this quantity kappa, or kappa squared, which is essentially the geometric mean of n times gamma and k, is kept finite. So you can see that there is a way to obtain the twisted warped action as a limit of the complex SYK model. Can we see such a limit also at the level of the asymptotic symmetry algebras? The answer is yes. So we see something analog to the inner-Wigner contraction that I showed you earlier when obtaining Bms4 from ADS3 symmetries. So let's start with the most general algebra that we have here. So the twisted warped Virasoro algebra. So this is warped width with all the three co-cycles switched on. So we have a Virasoro central charge C, a twist term kappa, and the U1 level k hat. And the complex SYK is governed by a symmetry algebra where the twist term is 0, but the other two co-cycles are switched on. And our model is based on the twisted warped algebra, which is sort of orthogonal to this case. So all the central charges that are 0 in the complex SYK model are non-zero here. So there's just one, namely kappa. And all the central charges that are non-zero in the complex SYK model are 0 in the twisted warped case. So C and K hat are both 0. And okay, I don't explain this in great detail, but you do this by first mapping between twisted warped Virasoro and warped Virasoro, which you can always do by shifting the central charge and shifting the 0 mode. And then you take a limit k hat to 0 and simultaneously the original C to infinity, but keeping fixed this quantity kappa so that this difference here tends to 0, so that you end up with no Virasoro central charge, no U1 level, but a non-trivial twist term that is finite. So to summarize the key steps, the CGHS model a la Kangemi-Chakif appears to be a nice bulk model for flat space holography. Here's again the action in the metric formulation. And if we impose asymptotically flat boundary conditions, we obtain Bms2 asymptotic symmetries. The boundary action, so the analog of the Schwarzian action, is this twisted warped action that depends on this time representation field H and on the phase field G. And this twisted warped action follows as a singular limit from the complex SYK action in the limit of large specific heat and small compressibility. And the same asymptotic symmetries also follow from a single limit of warped Virasoro. So we can also obtain BMS, or rather warped width, as a singular limit of warped Virasoro. So the upshot of this is that this model could be a useful toy model for flat space holography. So since 1 hour is almost over, I think I have 1 minute or so, let me come to the last slide. Here I present just a very brief outlook to future developments. So now that we have a concrete model for flat space holography in 2 dimensions, I think it would be nice to start establishing a dictionary. So calculate observables on the condensed matter side, calculate observables on the gravity side, and try to compare them with each other. One particular instance is to do cardiology. So by this I mean doing a microstate counting based on the twisted warped symmetries and see whether it correctly reduces the entropy. There are numerous other questions of interest. So basically any question that people discussed in the past 5 years in the context of SYK could be transposed to this flat space limit. So one particular example is the question of chaos bound saturation. It is known that the SYK model in the large n limit at low temperatures saturates the chaos bound, which is an indication that it can have a gravity dual. Is there something similar in the flat space limit? That's, I think, an interesting question. And last but not least, let me include also a line that I usually don't include in my talks, but here it may be justified. So in principle, there could be an experimental realization of this model because, well, it is arguably possible to come up with experimental realizations of the SYK model. And if you can tune your experimental parameters in such a way that the specific heat goes to infinity and simultaneously the zero temperature compressibility goes to 0, then you may have an experimental realization of our model. Okay, so that concludes my talk. Let me stop here and thank you for attention. And I'll be now available for questions. I'm not sure if I still have sound, so I might have to log out and log in again. So Mark, can you say something for a second?
Yeah, you lost your sound already half an hour ago.
Okay, I don't hear anything, so I lost my sound. So I will stop sharing now and leave and come back again in a second.
Mm-hmm.
Okay, so
Yes,
yeah, now I hear you.
Yes, now? Okay.
Yes, yes. Okay, thanks. Yeah, sorry for the annoying sound that you hear in the background. Apparently, there's some construction going on.
Yeah, it's not so bad. Don't worry.
Okay, okay.
Okay, so we can thank Daniel and maybe some questions for him. So I had a question. It was towards the maybe the middle of the talk. Once you introduced the BMS generators.
Right.
So I was wondering why I got a bit lost as to why what's the initial motivation for doing this change of generator and to get the warped algebra.
Well, the initial motivation may not be a very strong one. It's just that it's possible. And what it does, it changes the spin of your super translations. It changes from spin 0 to spin 1. And in the original BMS algebra, the spin of super translations was also 1. So if you want to have the closest possible analog to BMS4, then actually the warped width algebra might be a somewhat closer analog than what we call BMS2.
Mm-hmm.
So, I mean, it's basically up to us or up to the community to decide what you want to call BMS2, which spin you want to associate with super translations. Do you want to associate spin 0, spin 1, spin 2? You could also call all of them BMS2. And if you do this, then, well, then what I called warped width is just one particular instance of BMS2 that has a certain spin, namely spin 1.
Okay, but is this change innocent with respect to then how you realize this dynamically? Because it seems that the fact that
it's not completely innocent. I mean, as I said, it's almost a change of basis, but you know, almost is not exact. And more precisely, it means that if we use the warped width algebra, we neglect the possibility of winding modes, or we assume that there are no winding modes. So I think it's a pragmatic question. Do you want to allow for winding modes of your Maxwell field or not? If you do not want to allow for winding modes, then you should use warped width and not the algebra that I showed to you earlier. If you want to allow for winding modes, then it's better to use the spin 0 version rather than the spin 1 version.
Mm-hmm.
So that's, yeah. I think it's just a pragmatic choice. What is the precise physical application you have in mind? And is in this physical application, is it of importance to allow for winding modes of the Maxwell field or not? But other than that, I think you would be justified in calling either of those BMS2. It's just historically BMS is usually associated with spin 1, but I don't think it's a very strong reason to prefer one spin over the other.
Mm-hmm. Okay.
Maybe I can ask a question. Hi,
Sure.
Daniel, this is
Hi,
Sergey.
Yes.
Thanks
Hi.
for the nice talk. My question, maybe I missed some crucial step. Can you explain once more, what is the origin of the central extension of your algebra? Because there is nothing quantum, it seems.
That's true, that's true. There's nothing quantum. So this is a classical central extension in conceptually the same way as the Brown-Eno central extension is a classical one. So you don't get it from some normal ordering or something like that. You get it from the canonical realization of the asymptotic symmetries. So I skipped a lot in the introductory part. One could easily give a 1 hour lecture just on explaining asymptotic symmetries and their canonical realizations. So, but the upshot is that if you realize asymptotic symmetries through asymptotic killing vectors, then you never get central extensions. But if you realize them canonically on the state space through Poisson brackets of your canonical boundary charges, then you have the possibility of obtaining central extensions. That doesn't mean you necessarily get them, but you can get them. And this is precisely how Brown and Deneau obtained them. They obtained them through evaluating the Poisson brackets of the canonical generators of the asymptotic symmetry transformations. And they found that there's a non-trivial, but really classical co-cycle corresponding to a Virasoro central charge. Here it's the same. So in order to apply the gravity limit, or the supergravity limit if you want, we have to assume the Newton's constant is very small. But if Newton's constant is very small, then this parameter kappa that I showed to you must be very large. So it's a bit like the Chern-Simons level in 3D gravity.
But can you explain, what is the sense of this parameter kappa? So what is it precisely? Because it multiplies the central extension, yeah? So
yes. So I mean, the meaning of the co-cycle itself, it's a twist term. So it means that your spin 1 current, J, if you interpret it in a CFT context, it's not going to be a primary, it's going to be a quasi-primary. And sort of the strength of this twist term is parameterized by this value of kappa. On the gravity side, kappa is just inverse of Newton's constant. So in the gravity limit, kappa is a very large number. So again, with the same features for Brown and Deneau, the central charge is not a small quantum correction. It's a dominant classical piece. Yeah.
So can one say that you kind of have some freedom in your model and you switch on something which describes this freedom, which generates this central extension?
I mean, the freedom is the freedom to impose different boundary conditions. But once you have imposed our boundary conditions, there's no more freedom. So it's not that you can tune the central charge or change it. It has precisely the value that I gave to you. So it's given by this kappa, where kappa is this quantity that appears in the action as a prefactor. Again, in the same way as it happens in the Brown and Deneau case. So there, once you commit yourself to Brown and Deneau boundary conditions, you have no freedom in choosing the central charge. It's just given by 3L over 2G. I mean, you can choose the value of Newton's constant, of course, to make it bigger or smaller. But other than that, it's determined. And the same is true here. So it follows from, for instance, a canonical analysis that this co-cycle is non-trivial and it has this precise value. At the same time, the other two co-cycles which could have been there turn out to be not there. So there's no Virasoro central charge, even though, you know, algebraically it would be allowed to be there. And there's also no U1 level, even though, again, algebraically it could have been there, but it turns out that it's not there. And that's, again, somewhat similar to the Bms4 case. Also in the Bms4 case in Einstein Gravity, Compare and Barnich, they found that there could have been a Virasoro central charge algebraically, but for Einstein Gravity, it turns out that there isn't one. There's only a mixed central term, which is a bit reminiscent of where the central term appears in our model. It's in the mixed commutator between super translations and super rotations.
So the U1 central extension in the 2D case is a bit analogous as the one in BM3 you would get from a massive term in TMG?
I guess that's true. I don't know if there's a model that switches it on. So that's actually a very good question. I haven't come up with any candidate for such a model. You're right. In 3D gravity, if you don't consider Einstein gravity, but some massive gravity model like TMG, you switch on the Virasoro central charge. That's absolutely correct. And therefore, it's conceivable that there are two-dimensional dilaton gravity, or I don't know if dilaton gravity, but some 2D gravity models where you can switch on the Virasoro central charge, but we have not been able to identify any such model. I mean, I don't want to claim there's a no-go. Certainly there isn't. We didn't just look hard enough for models where you would have such a Virasoro central charge. They may well exist, but I don't know any such realization. I don't know any such model. Yeah, it's a good question. Yeah.
And then at least algebraically, if you had such a model, could you have something like the Galilean conformal algebra in 3D, but a 2D version of the different
Galilean conformal algebra in 2D. That's an interesting question. I mean, in some sense, you may say this is the Galilean conformal algebra. But I'm not sure if this is justified. So I guess it depends what you mean operationally by Galilean conformal algebra in a 2D gravity context. I mean, on the field theory side, it would be Galilean conformal algebra in 1 dimensions, and I'm not sure what this means precisely, right?
But from
I mean,
and from the point of view of which central charge you get as your flat limit of the.
From the point of view of which central charge you get, it's reminiscent of the Carolean conformal algebra rather than the Galilean one. So the Galilean is like the non-relativistic limit. Here, what we're doing resembles more an ultra-relativistic limit, which I think makes sense because a naive way of picturing what happens or how you can obtain flat space from ADS is you take the ADS cylinder and you boost it until you hit the light cone, and that light cone is basically scry. So in this way, you can understand why, if there is a limit of this sort, it should be an ultra-relativistic limit, a Carolean limit, and therefore you expect Carolean symmetries. And this is indeed how you can understand Bms4. So Bms4 is isomorphic to the Carolean conformal algebra in 2 dimensions. It's just a bit confusing in 3D because the Carolean and the Galilean conformal algebras are isomorphic to each other. So they're physically inequivalent, but algebraically isomorphic, which sometimes leads to confusion.
If I can jump on that, what would be, I mean, how you would have a Carolean structure actually, because you don't have
I don't know, you don't have space enough, right? If we're into the
you don't have the metric, which is the somehow core of the, but maybe
yes.
the which.
So that's what I mentioned also in these caveats to BMS2. So it's not clear if you have enough space in the first place to get something like super translations or super rotations. But well, I would say that the algebra that we find can justifiably called BMS2 in the sense that we do have super rotations in the sense of having diff S1 if we're under this. And we do have super translations in the sense of having infinitely many mutually commuting generators. But of course, they are geometrically very different from the super translations that you're used to from higher dimensions. There's no spatial directions at the boundary. So there's no angle dependence that you can have. And therefore, I agree with you that it's not clear geometrically what Carolean even would mean in this context. Yeah. But the notion of an ultra-relativistic limit still makes sense in 2 dimensions, right? Because your ADS boundary is a time-like boundary, and you can just say, okay, I do an ultra-relativistic boost. What do I get? Well, I get scry. So that analogy still works. Whether you can meaningfully push this further, I mean, if you just want to give it a name, you might call it Carolean. But the question is there more substance to this name? So can you find more to this Carolean structure in 2 dimensions? And well, within standard dilaton gravity, I'm not sure, but there is Carolean version of dilaton gravity, which you can obtain as limits of dilaton gravity. That's a separate story. That's a story that, well, you can find in this work with Jakob and Jelle and Stefan. But yeah, in the context of relativistic dilaton gravity, I'm not sure there's a meaningful Carolean structure at the boundary, but maybe there is, I don't know.
Mm-hmm. Okay, thanks.
Sorry, Daniel, my computer collapsed.
Okay, yeah, okay.
But I think I understood the answer anyway. Yeah.
Okay. If not, it's recorded anyhow, but yeah. Okay, good.
Okay, are there more questions? Right, if not, well, we can thank Daniel again.
Okay, thanks.
Thanks again, yes. And
see you some other time.
Yeah, and just to advertise, so there will also be a kind of exceptionally, but another talk on Thursday by Laura Donnet. So also in this series, you can join with the same link. Okay, so thanks.
Okay, thanks. Bye-bye.
Bye.